Welcome to lesson 3 of our relational database design. And this lesson we're going to look at the extended entity relationship model, or call it the extended entity relationship diagram. This is how the lesson is laid out. We have an introduction, we have extended ERD features, which include the subtypes, the supertypes, specialization, generalization, overlapping, disjoint constraint, completeness constraint, which involve total and partial. And also we have an example, an extended ERD. And also, lastly, we basically look at the relation schemas in extended ERDs. Introduction. The extended ERD or ER model. This is also an enhanced version of the traditional ERM, entity relation ERM, and it extends capability of the traditional ER model by introducing new features. These new features represent complex relationship and constraint more effectively. The features include supertypes, subtypes, generalization, specialization, overlapping, disjoint constraint, and completeness constraint, which is total and partial. Entity subtypes and entity supertype. Both these entities are used in modeling hierarchical relationship. And the supertype entity is also regarded as a high-level entity, looks at general aspects of an entity. It has common characteristics of a low-level entity, and low-level entities are basically our subtype entities, and they look at specialized aspects of the entity. The subtypes inherit all attributes and relationships of a supertype entity. The relationship between the supertype and the subtype entities is also regarded as an is-are relationship. This is a basic example of an extended ERD. We've talked about supertypes that appear at high level at the hierarchy. So you can see a person is a supertype, and we have subtypes which are basically underneath, pointing towards the parent or the supertype entity. We have 4 subtypes: student, staff, TA, RA. And TA is basically a teaching assistant in this case, and then RA is the research assistant. We talked about inheritancy with the is-are relationship, meaning that we inherit the attributes together with the relationship. And the inherited relationship here that the parent has with the dependent is basically the person has dependent. And the dependent can depend on one person. Dependent in this case is a weak entity because of the primary key. Its attributes cannot uniquely identify it. So it needs a primary key of a strong entity, and that's why you see the primary key of person ID appears in the weak entity. Specialization and generalization in extended ER model. So specialization is basically a top-down design process. When you look at the diagram right over here, you see the specialization appears an arrow showing down. That means from our high-level entities to a bottom-level entities or low-level entities, the design process we assume is basically the specialization. And what does it involve? It basically involves a grouping unique characteristics and relationship of subtypes. As you go down the hierarchy, each of these entities are grouped based on their unique characteristics. Let's get an example. Entities, records in person, we get records that are specialized as student, and we group them as student, and we get records that are specialized as staff, and we group them as staff. The same thing happens to our bottommost hierarchy or level, where we get records in students that are specialized or that are unique in TA. We group them as TA, and then we get records that are specialized as research assistant, and we group them as such as assistant. Generalization. Generalization is basically the opposite, and that means it's a bottom-up design process. And the grouping here is not going to be looking at unique characteristics, but it's going to basically look at the common characteristics, basically general characteristics, and it's a bottom up. It basically starts from the low-level entities going up the entities to the supertypes. Let's get an example. As we go up generalization, as we go up our design, we form records that are found in students basically are common in TA and common in RA. The same thing applies in person. Records that in person are common in student and at the same time common in staff. Overlapping and disjoint constraint. Overlapping subtypes. When you look at the diagram, we have 1, 2, 3, 4 subtypes. Overlapping subtypes are indicated by separated arrows from subtypes. The separated arrows from subtypes, when you look at the arrows coming from our subtypes, are basically these arrows. There's this one, and then we have the merged one. The separated means these are the separated arrows. This is how we know that these subtypes are known as the overlapping subtypes. Each of these subtypes contains common subset of a supertype. And what does this imply? This implies that an instance in a supertype person can be found in either student or staff. So you can say that a person can be both staff and student. Let's get an example. Person with ID 1 can be found in student, can also be found in staff because of the overlapping aspect. Disjoint, or even call it the non-overlapping. Disjoint or non-overlapping subtypes. These are indicated by looking at merged arrows coming from the subtypes. When you look at these arrows are not merged. When you look at these arrows from the subtypes are merged. That means these two entities are known as disjoint subtype entities. Each of the subtype entities have unique subsets of a supertype, meaning that an instance of a student can only be in one of these. This implies an instance or a record in student can only appear in one of these. For example, student ID 1 can be a TA but cannot be an RN. And you can say that a student is either a TA or RA, but not both. Completeness constraint that involves total and partial. Completeness constraints specify whether a supertype or currency is a member of at least any of the subtypes. Total completeness is indicated by dotted lines cutting across the arrows from the subtypes. Every occurrence must be a member of at least one. Let's take an example of two records of person. Record 1, which is Peter, and record 2, which is John. The two records are said to be in total completeness if they are fully utilized, if they appear in any of these entities. Partial completeness, which is also the default one, and not indicated with dotted lines. This implies some of the supertype or currency need not to appear in any of the subtypes. Let's get an example of the two records, Peter and John. Peter and John do not need to appear as student in either, do not appear as a student or staff. If one appears and one doesn't appear, still it's partial completeness. Relational schemas in extended ERDs. When you look at the extended ERD, we have 1, 2, 3, 4, 5, 6 entities. And we start with the parent entity, which we also call the supertype entity. Person. Having person's ID, first name, last name, and birth date. When we're representing it as a relation schema, we have to write the name of the schema first, person, open parenthesis, person's ID, first name, last name, and birth date. Don't forget, in the relation schemas, we indicate the primary keys, and it must be underlined. After fully representing this relation or this entity or this table in relation schema, we go to the next, which I categorize as subtypes. We have 4 subtypes. Let's begin with student. When you're writing the relation schema, you start with writing out the name of the entity, which is student. Student is right here. Person's ID. We have first name, last name, birth date, and department. The question is, where are these coming from? They're coming from the is-er, which is an inheritance. So meaning that we are inheriting all the attributes that belongs to my parent, that belongs to the supertype. Okay? And that is why our relation schema in student have all the attributes that belongs to our person's attributes. Don't forget to include the major and GPA that are unique to a student. Same applies to staff. Write out the name of the relation staff and all the other attributes that are inherited from its parent. And that is person's ID, first name, last name, birth date, and its independent attribute, which is department. One thing you need to note is the primary key is also a foreign key. That's why we label it as a PK and an FK in each of the subtypes. PK and the FK. Remember, an entity cannot exist without a primary key. TA is written out the same way. The TA, which is the name of the entity, and all the other entities that are inherited from the parent entity, including its own unique attributes, which is hours and credit. And also RA, we use research assistant. We write out all the entities that belongs to the parent, including the primary key, and also its unique attributes, which is basically the date and the topic. We have another entity that comes from a relationship that our parent has with another entity, and we labeled it a weak entity. Okay, being an entity as well, we also represent it the same way we represent all the other entities. So we write out the name of the entity, which is dependent. Now pay attention on the primary key. The primary key here is a combination of its parent or its strong entity, which is the person's ID, and its weak primary key, which is the department ID. If we combine a weak primary key and a strong primary key, the combination becomes a strong primary key. And of course, we also include all the other attributes that are unique to the dependent. Weak and strong entities. We define the weak entity as an entity that cannot be uniquely identified by its own attributes alone. That means it depends on the existence of another entity, and that entity is a strong entity, is the parent entity. You can also say that its existence is existence dependent, and this basically means the existence is dependent on another entity. The primary key in the weak entity must be derived either partially or totally from a parent entity. And of course, when you look at the diagram on the right-hand side, we see that the primary key is a combination. Okay, it's not two primary keys; it's a combination, which I say a person's ID plus. This is one primary key that's been combined into one, and we call that a composite key. The relation schema is the same relation schema we derived earlier on. A strong entity can be uniquely identified by its own attributes without depending on any other entity. And you can say it is existence independence, meaning its existence does not depend on the existence of any other entity. Weak and strong relationship. A weak relationship or a non-identifying relationship is a relationship when the primary key of a weak entity does not include a component of a parent entity. For example, if primary key of the dependent does not include a primary key of another entity, then we say that is a weak relationship. However, a strong relationship, which we also call the identifying relationship, is a relationship when the primary key in a weak entity includes a primary key of a strong entity or of a parent entity. An example in our diagram is if a primary key independent, includes a primary key of another entity, person's ID, person ID, then that is a strong relationship, or it's an identifying relationship. And of course, the relation schema still remains the same for our weak entity. Representing composite attributes in relation schema. When you look at the diagram, we identify our composite attribute as author name. And why author name? Because author name can have a first name and a last name. So each of these components must be broken down into single valued attributes. And this is how we break it down. Each of the components is going to be renamed. It's going to be labeled. We're going to label the first component of our composite component as the name of the composite component, which is the author name underscore first name. So basically, you're going to append the name of the composite component together with its component. Last name becomes the author name, which is the name of the composite component, underscore last name. Now, the naming convention can be different as long as it is descriptive enough. Relation schema, how does a relation schema turn out to be? Because we have these are now fully fledged single valued attributes, we treat them as regular attributes in the relation schema. And you can see that now we write out the name of the relation, which is author, then the primary key with the author ID, the author ID underscore first name, which is basically a translation that we've just done of composite attributes, author name underscore first name, author name underscore last name, and the birth date. We've taken a combination of this as fully fledged single valued attributes, followed by the birth date. The question is, where is date and where is contact information in our relation schema? Let's start with age. Age is a derived attribute, and in practice, derived attributes are never included in relation schema for some reasons related to time variance. Contact information, which is a multi-valued attribute, needs to be handled differently, and we're going to see that in the next slide. Representing multi-valued attribute, which I'm going to label as MVA in the relation schema. The approach here is to combine the primary key of the entity containing the multi-value attribute and the multi-value attribute itself. Okay, they must form a new relation, and of course the combination must become a primary key. Let's go step by step. The first step, let's see what's the primary key of the entity containing the multi-value attribute. Is the author name. This is the entity that contains the multi-valued attribute. These are the multi-valued attributes. So we're interested in the primary key of that entity, which is author ID. We put it aside. Then we look at the multi-valued attribute, contact information. Contact information is multi-valued, and we labeled it with the curly brackets. We also put it aside because we want to combine these two and form a new relation. So our new relation must first of all have a name. Okay, we're going to get the name of the entity, which is author, and the multi-valued attribute, which is the contact information. And we combine them with author, the author underscore contact information. The naming convention can be different as long as it's descriptive enough. The relation schema is a combination of the entity name and the multi-valued attribute. And you can see here my entity name is author and the multi-valued attribute is contact information. And of course the combination of author ID, which is the primary key of that entity, and the multi-valued entity become a primary key. So we are going to underline all that, and this whole thing is going to be our new relation. Let's test this new relation. Let's assume author ID 111111 enters two records of the contact information. Take a contact information, the phone number. So phone number 234 and phone number 345. This will appear in two tuples. Tuple 1 is going to be 111 plus 234. So these are two different tuples. And you can see that when you combine this as a primary key, we are still getting a unique tuple. And that means that our new relation does not violate the relation integrity. To represent this information, we'll have two schemas. The first one with author without the multi-valued attribute. We're going to basically write out the first relation schema without the multi-valued attribute, because the multi-valued attribute has formed an entirely new relation schema. And you can see right over here our new relation schema, which is basically author underscore contact info with the primary key of both, combination of the primary key of the entity containing the multi-valued entity and the multi-valued entity. They become a primary key in a new relation. ER design issues. Let's look at ER design issues, and these design issues may call for designer expertise in order to make a good judgment on their design. The first one, we want to look at entity sets versus the attributes. You're going to reach a point where you need to decide in your business rule, are you going to use an entity or should you use an attribute? And of course, some of these depend on that. Some of these decisions depend on the structure of the enterprise or an organization being modeled. Let's look at the first case. So the first case, if an organization wants to collect only one phone number, someone can say both of these designs can work. Okay, so it's one-to-one because this is one-to-one design, and we've explained all this in the previous lesson. If you're entering only one phone number, you can use either of these design. Preferably, the second one would do best. Now, if you go to case 2, where you want to collect more information on the phone, probably you want to look at the type of the phone, or you want to look at the service company of the phone. So you find that this may not really be sufficient enough because the information you're collecting is not pertaining to author, but is basically on the phone. So you basically going to go with the second. And of course, this will turn out to be multiplicity. The cardinality here is going to be an asterisk, which stands for many. Okay. And of course, and then the third case, when you want to collect more than one phone number, still this will work best. The second design issue that may come up when you want to decide whether an object is a relationship or an entity. An example in this case would be a customer has a loan of a particular amount in a branch. So a loan is participating in the relationship. You want to know whether that loan is actually an entity or it's a relationship. So for this case, since a loan has other attributes like a particular amount of the loan, we recommend that you can create it as an entity of its own. And of course, the best approach is to have a loan appearing as an entity as opposed to a relationship. Another common design issue comes from whether deciding a binary type of relationship or a non-binary type of relationship, which we also call the n-ary, n meaning the number of entities participating in a relationship. Binary is basically two entities participating in a relationship. For example, this is a binary because it has two, and this is ternary because it has three entities participating in a relationship. So, for example, the relationship here is father entity is a father, okay, and then is a father parent. Mother is a mother who is a parent, and the child is a child of a parent. And this can be basically represented as a binary, okay, as a binary way, and we say parent is a father of a child, and can also be a parent is a mother of a child. Although there's some relationships that are naturally non-binary, you cannot break them down into a binary. But preferably, if a relationship can be broken down into binary, that will be a good design decision. The last design issue is when you're deciding where to place the relationship attributes, which we call placement of relationship attributes. And it depends what type of relationship you're looking at. And if we take an example of a customer makes deposits to an account, that's the relationship between a customer and an account is a deposit. But they say each deposit records the date of the deposit and the deposit amount. What does it mean? If you ever get such a scenario, you're going to look at the type of a relationship. For example, a customer makes deposits, and these deposits can be at least one deposit, or it can be more than one deposit. And where do we place the attributes? The attributes that in the relationship are date and amount. If you are ever stuck and you don't know where do I place these attributes that are in the relationship, you basically need to look at the many side. And in our previous lessons, we have indicated, okay, the second number in the notation is the one that tells us the type of the relationship. For example, this is a one to many because of the second relation. The asterisk stands for many. The asterisk stands for n, which means any number. Okay, so this is the one to many type of relationship, and this means that we have to move those attributes in the relationship into the many side, and that is why you see the attributes being moved. The deposit date and the deposit amount are being moved to the many side, and this is the many side and this is the one side. When you are looking at the one-to-one, it's different. Either way can work. So you can move the deposit date and the deposit amount either in customer or in account. Lastly is the many-to-many relationship, and this is very strict because it requires you to introduce a new entity, which we called a bridge entity in our previous lessons. And you can see that the deposit becomes a bridge entity with those entity in the relationship. Of course, we're going to see the deposit date and also the deposit amount in that relationship. Activities: find the enrichment activities on extended ERDs in the assessment section. Attempt 2 activity 3.1 and 3.2. That's the summary. It shows you layout of everything that we talked about. And our next lesson is going to be functional dependency in relationship database design.